In this video, I'm going to be talking about another approach for event extraction, and we are using this zero-shot learning. So I'm going to be explaining this paper in 2018. Most previous supervised event extraction methods have relied on features derived from manual annotations and thus cannot be applied to new event types without extra annotation effort. We take a fresh look at event extraction and model it as a generic grounding problem, mapping each event mention to a specific type in a target event ontology. We design transferable architecture of structural and compositional neural networks to jointly represent and map event mentions and types into a shared semantic space. Based on this new framework, we can select for each event mention the event type which is semantically closest to its space as its type. By leveraging manual annotations available for a small set of existing event types, our framework can be applied to new unseen event types without additional manual annotation. So this is an example of event mention. For example, here dispatching is the trigger of a transport person event. We have 4 arguments here, and you see the solid lines show the event annotations for the sentence, while the dotted lines show the abstract meaning representation parsing output. This is another example from ACE. You see the structure, event mention structures. Also, you see the type structures. For example, this type structure attack is related to time, place, instrument, target, and attacker. So these are the arguments of attack. So this is the architecture. The blue circles are event types and their annotations. The dark gray diamonds and circles denote triggers and trigger representations from training set. The light gray diamonds and circles denote trigger and trigger representation from testing set. So we distinguish between those training and testing. And here we are doing the grounding, because we know that the test event mentions donate has these arguments. So here we overview the phases involved in building our framework's shared semantic space. That in turn is the basis of zero-shot learning frame. So given a sentence S, we start by identifying the candidate trigger and arguments based on abstract meaning representation. After this identification phase, we use our new natural architecture to classify triggers into event types. For each trigger, we determine its type by comparing its semantic representation with that of any event type in the event ontology. In order to incorporate the context into semantic representation of T, we build a structure S sub T, again using AMR. So we have a tuple like dispatch and then argument 0 and then China. We use a matrix to represent each AMR relation, composing its semantic with 2 concepts for each tuple. So given target event ontology, for each type, for example, transport person is a type, we construct a type structure S sub y consisting of its predefined rows and use a tensor to denote the implicit relation between any type and argument row. We compose the semantics of type and argument row with the tensor of each tuple. Then we generate the event type of structure representation using the same convolutional neural network. And you see the event-related AMR relations. So the core rows are argument 0. In AMR, we know argument 1, argument 2, 3, and 4. But there are non-core roles as well, such as location, such as topic. And there are temporal categories and spatial categories as well, such as path, location. So for each tuple in an event mentioned structure, we use a matrix to represent each AMR relation lambda, and compose the semantics of lambda between two concepts, W1 and W2. And these are vector representation of words W1 and W2. And D is the dimension size of each vector, and this is concatenation as usual. M lambda is matrix representation for AMR relation lambda. So for each tuple in an event type structure where Y denotes the event type and R denotes an argument row, we assume an implicit relation exists between any pair of type and argument, and use a single and powerful tensor to represent this implicit relation. So these are vector representation of Y and R. This U is a 3-order tensor. Then we do trigger classification for scene types, and we use convolutional layer. So we take S sub t as an example. The input matrix of S sub t is a feature map of this dimensionality. And a convolutional operation involves a filter W, which is applied to each sliding window C sub I. So this is a sliding window C sub I, and you get the new feature representation. And B here is just bias vector. Then we do max pooling. Then we do learning. To train composition functions and convolutional neural networks, we consider the following hinge ranking loss. And this C sub T and J is just the cosine similarity between them. The hinge loss is commonly used in zero-shot visual object classification. However, it tends to overfit the scene types in our experiments, while clever data augmentation can help alleviate overfitting. We design two strategies. We add negative event mentions into training process. Here a negative event mention means that the mention has no positive event type among all scene types. Namely, it belongs to other. And we design a new loss function. This is the new loss function. And Y here is the typeset of event ontology. But Y prime is the type which ranks the highest among all event types for event mention T. And then we do argument classification for scene types. We apply the same framework to take sequence of tuple contained in S sub A and S sub R, because S sub A is just a path which connects T and A. And then we apply the same framework. During test, given a new event mentioned T sub prime, we compute its mentioned structure representation for S sub T prime and all event type structure representation using the same parameters trained from scene types. Then we rank all event types based on their similarity scores with mentioned T prime. So this is the case most probable event type predicted for T prime. After determining the type Y prime for mentioned T prime, for each candidate argument, we adopt the same ranking function to find the most appropriate role for the role set defined for Y prime. And you see scene types for training and development, such as attack, die, and these things. And the parameter name, for example, for word sense embedding size, it has value 200. So we have trigger classification and argument classification. And this is the accuracy for them. So this table shows comparison between structural representation and word sense embedding. So here is the impact of AMR and semantic roles. On, for example, you can see the F1 score. You see the amount of impact for AMR and semantic roles. So in this work, we propose a transferable neural architecture which leverages existing human constructed event schemas and manual annotations for a small set of scene types and transfers the knowledge from existing types to extraction of unseen types to improve the scalability of event extraction as well as to save human effort.